Okay, welcome all. I will talk about two things. On the one hand, light field imaging that has caused quite a stir in recent years, and then a brief introduction to compressive sensing. But before we go into the light field stuff, a reminder of pictures that you know from high school, or at least I have them from physicsclassroom.com. So it will all be about ray optics today. No quantum effects, no diffraction. And we have here the thin lens model of a camera. We have an object that is in focus. So we have the object here and the sensing plane there. And in this schematic picture, you see, if we look at the red ray, for instance, maybe I should take a different color. So this ray is mapped to this point on the sensing plane, and that ray is mapped to the same point in the sensing plane. So we have a sharp image. And as far as ray optics is concerned, really a point is mapped to a point. If we did consider the diffraction, which we don't, we would see a point spread function convolved with the actual point under observation. By the way, in a camera, we don't have a single lens, but depending on what you buy, 3, 4, 5, this is especially required if you want zoom lenses, because if you did use just 2 lenses, which is a very simple setup, you would you would not be able to zoom, and if you use a simple lens setup, essentially you get many aberrations, especially towards the fringes of the image, and the extra lenses are required to compensate for all of these aberrations. Now let's look what's happening if an object is out of focus. I could either move the object and keep the sensing plane, but in this picture here it will be easier for me to just move the sensing plane. So let's say the sensing plane is now at this location here. And if we again consider the 2 green lines that I have just scribbled here, we now have one of the green lines impinging on the sensing plane here, and the other green line impinging on the center plane there. And instead of the point, we would now observe the circle of confusion, which is the image of our aperture. And in most cases, this aperture, well, is formed of a couple of half plates that can be rearranged to form a larger or smaller hole. And the image of this aperture, if we had just a point source, is what we would now see at this point. And I'll show you a picture later on. So things eventually go out of focus, and how far they go out of focus depends on the size of the aperture. So here's an image of an object on which the lens is focused. So the point that I've just indicated is mapped to a point on the sensing plane, and the point which is further away is mapped to a whole interval here. Again, this is a circle of confusion. And we can now study what's happening if our aperture becomes larger or smaller. For example, if I artificially restrict my aperture to become smaller, so that all of the light out here is blocked, Then looking again at this outer focus point, the most extreme rays would be this one and that one, and the resulting circle of confusion would be somewhat smaller. And if we carry this further and further and make the aperture smaller and smaller, we end up with a pinhole camera, which is in focus everywhere, but hardly lets any light through. So this is why if you really build a pinhole camera, you have such long exposure times. So here, two pictures from Wikipedia. Same scene, but acquired with a small and a large aperture, respectively. And what you see at the bottom, using such a large aperture, that's of course a frequently desired effect when if you want to take a portrait of the flower, then you don't want to be distracted by all the stuff in the background. But sometimes you also want a picture that's sharp everywhere. And the trade-off is, how much light passes through your aperture, so how long it takes to take the whole picture. And the region which has an acceptable circle of confusion that's not too large is called the depth of field. I learned Tiefenschärfe in German, but I read that actually Schärfentiefe seems to be the proper word. Has anyone ever heard the proper word? No? Okay. Anyway, supposedly that is the proper word. Admittedly, it makes more sense, but I've never heard it. So if you specify the circle of confusion, if you say this is the acceptable circle of confusion, then you can compute how far apart the objects which are still rendered in a sharp way can be. And here we have again a large aperture, and then the depth of field is relatively shallow, or for a narrow aperture it becomes wider, or for an even narrower aperture the depth of field would be larger still. Okay, so this as a reminder. And now about light fields. Let's see if we have internet here. This is a short movie from the camera array page at Stanford University. This is one of the labs headed by Mark Levoy that has been a leading developer in all of this light field photography. Let's repeat this. This is a whole array of lenses that is standing in front of a hedge, a couple of bushes. And as you perform a series of computations, you can actually see through the bushes. Scary, isn't it? However, to achieve that, you need a rather large baseline. So you need ideally many cameras that are spaced far apart. There are also much more compact versions of cameras to acquire such light fields, but as I will show today, these are restricted to a much smaller range of things that you can image. So here is my favorite paper in all of light field analysis. The picture comes from a paper by Anat Levin, Bill Freeman, and Fredo Durand. And Anat told me that she actually had trouble getting this paper accepted. And this is my favorite picture in the whole field. So I don't work actively in light field. So when I don't teach about it, I forget what it was. And then when I come back 2 years later and need to understand it again, then I just stare at this picture and it says everything. Okay, so we will spend a lot of time studying this picture. So first of all, what is a light field at all? Obviously, a flat 2D camera image does not tell us everything there is to know about a scene. So if we want to explore a scene, we typically move around in space. And if we capture a light field, a four-dimensional entity, then we can imitate or we can reproduce this walking around in space. Actually, there is even more to know about a visual scene. A few comments on that later. So there are different. So the essential difference is the following: that in a normal picture, in a normal photography, we just count how much light arrives at a single pixel, and we record the color also. Whereas in a light field, we want to know how much light and where does it come from. So we need to parameterize this extra degree of freedom. So we have 2 degrees of freedom. So one frequent parameterization is as follows. We have 2 spatial coordinates to index our pixels, and then we have another 2 dimensions to index or to explain where the direction, what direction a ray comes from. So for example, if I have this coordinate here and that coordinate there, then I know that my ray came from this direction. So we have an entity that is altogether 4-dimensional, and because it's always hard to draw things in 4 dimensions, we restrict ourselves now to just one spatial dimension. And this is what in the figure is called the A plane and the B plane, with the 0 here being in the middle. And we can now index each ray. So for example, the ray that I've just shown here would be, let's say, at A equals 1 and B equals 1. So the ray that I've just shown corresponds to one point in this AB plane. Okay, so the particular ray that I've just shown, for example, would lie here at A equals 1 and B equals 1. And this ray would lie at A equals 2 and B equals 2. It would be up here. And let's look at this ray. So A is 0 and B is 1. Would be this point here, and so on. Note that here the y-axis is called A and the x-axis is called B. Okay, so this is the kind of parameterization that we will talk about. And we now have this object on the upper left. Again, the origin is in the middle. And we can now index any ray by its A and B values. And if we now look at all possible rays and what an observer at the end of the ray would see, this gives you the light field shown in the second image. So let's start with something simple. Let's say, so the objects, the red, green, and blue object are considered opaque. And if I have, let's say, this ray here, and an observer, this is meant to be an eye, looking at the ray, we are at A equals 0 and B equals 0. We're just at the transition of the blue and the green object. If I move my observer a little bit to the right, so we're looking at this ray here, here's the eye, then A and B both have some positive value. For example, so that means we're at this point here in the light field. And there are now many other points that show us the equivalent, or many other rays that show us the identical same point. So we would, at the end of, if I had the patience to draw an eye at the end of each of these rays, we would always see the same green color. So what's happening is that we have a constant B value, but different A values. Constant B value, but different A values. This translates to this line here in my parametrized picture. And of course, at some point, when I start to put my eye here far out, because the objects are opaque, I now start to see something that's blue. And this is exactly, if I'm choosing a different color here, so let's say, oh, yeah. So this is exactly what's, you can't see that either, huh? Let me take red. This is exactly the blue values that you observe down here, is I consider more and more extreme rays that are all pointing here at the same, that are all intersecting the B plane at the same position, but I'm seeing different parts of the blue object. Okay, so by looking at this bundle of rays here that has all intersected the B plane at the identical location here, we have now investigated one particular column of this light field. And similarly, I can now consider all possible rays, and all possible rays correspond to all points in this two-dimensional diagram. And I can always record what my eye, which has a single pixel because it looks at a single ray, what it would see at the end of this ray. And altogether, this gives you this picture here. Now, if we step back a little, we see that, the green object, because we centered the B plane right on it, the green object has a signature that depends on the B values only. So we have a structure that looks vertical in this plot. The A object is closer to us, closer to the observer, so it gives rise to a slanted surface, and the red object is further than the B plane, so it gives rise to a surface or to a manifold that is slanted in the opposite direction. So when we look at opaque objects, for the moment, let's assume that they're opaque and that that our depth image is piecewise constant. So what this translates to is a couple of occluding, should I say, manifolds or patterns, the orientation of which reveals us the precise depth of the object. So if I'm looking at the angle here, this angle translates to how far away is the object. Now this is a 2D, this is a scene with just one spatial dimension, so I needed only 2 indices. In reality, of course, I have 2 spatial dimensions and altogether 4 indices, and I would need to draw a higher dimensional picture really, which I don't for now, or which the others don't for obvious reasons. Okay, any questions about A and B? We have not talked about any imaging device yet. I really only need to say, so if I consider some ray, like this one here, I really only need to specify on which end of the ray the observer is sitting. Because if the observer is up here, she will see red, and if the observer is down there, she will see blue, because the objects are opaque. However, the observer just needs a single pixel, because the observer is just looking at a single ray. Okay, so one ray coupled with its one observer corresponds to a single element here of my light field. Yes, you are right when you talk about focus, in the sense that things that follow a purely vertical pattern here, this is what I like to think of as being in focus. Okay, so you just thought further than I did. Did that answer your question, or do you have more? More questions on this one? I'm asking so explicitly because we will spend, at this pace, we'll spend probably 2 hours, not quite, on this picture. Okay. Then let's look at the pinhole camera. And I'm showing a slide here from the original talk that Anat Levin gave in, I think it was ECCV, but I'm not sure, 2008. So on the left side of this picture, you see repeated the set of objects and the rays. The rays are here colored just for identification purposes. And in this case, the aperture has been put directly in the A-plane, and in a perfect pinhole camera, this aperture would be infinitely small. So we know that all of these rays have the same, I'm confused, A value, B value. Yeah, so A is constant, and we only have variation in B. I was again confused with A not being the x-axis, and it's the only thing I found counterintuitive about the plot. Okay, so A is constant. In this case, A was put at, or the 0 was put at this position here. So A is 0, and we just have different values of B. And for each of these rays, for the different values of B, we have here our sensor elements that see different parts. So the first sensing element, this one here, it sees nothing at all because there's no object. So this is the white one here. Then the next sensor element, if I give it a number, this here would be sensor element number 2. It already sees the red object. So this is exactly what this second sensor element number 2 sees, and so on. So each of these rays corresponds to one of the sensor elements. And these sensor elements have some extent in both the A and the B direction. In the B direction, because each sensing element in itself has some finite width. And because the aperture also has a finite extent, we also have some spread of our sensing elements in this vertical direction here in the light field sketch. So each sensing element integrates the light field over one of the boxes that's shown on the right-hand side. And the boxes cannot be made infinitely small. So if we use a super thin pinhole, and if we use a super small sensing element, then on the one hand, it looks like our measurement becomes more and more accurate because these boxes over which we integrate shrink. But on the other hand, if you remember that we have Poisson noise and so on, it means your measurement becomes too noisy. So this is a compromise. If you make your pinhole too small, you capture too little light. Same with the sensing element. So our pinhole camera samples the light field in this direction here, always integrating a little. So in that sense, smoothing a little the true light field that we see. And everything is equally well in focus. So we see the blue object just as almost just as sharply as the green object and so on. So this is the pinhole camera, and this is the part of the light field that the pinhole camera samples. So we see everything pretty much in focus, but we have no depth information whatsoever. Next, let's move to D, to the lens. Again, a slide from Anat's talk here. Shown here is a lens which again lies in the A plane, and it is focused. It has the right distance from the sensor plane such that a point in the sensing plane is mapped to a point in the B plane. And we can now look at these individual rays one by one. So there is, let's look at so if we look at the path that was mapped here, it corresponds to, oh, that was poor accuracy, corresponds to this ray. So this is amongst this bundle of rays. So I have two extreme rays here, and everything between these two extreme rays is mapped to the same sensing plane by my lens, which has a pretty large size. So the extreme ray, which I'm going to call ray number 1, has a relatively large value for A, and they both have the same B value. So ray 1 sits somewhere up here. And then I have this other extreme ray, ray 2, which sits somewhere there. However, this single sensing element captures all these rays that are intermediate between these extremes. So those are these positions here. Because we have a single sensing element and do not resolve where each of these rays came from, we see just a single box here. So this is, if we use a lens focused on the B plane, this is what part of the light field is integrated over by the purple sensing element here. And similarly, every other sensing element integrates over such a box in this 2D light field space. Okay, so the green sensing element integrates over this box, and the yellow sensing element integrates over that box, and so on. This was the proper one. So back to big picture here. The 2D lens does not blur my picture, does not blur the green object at all, because the green object is oriented in a perfectly vertical fashion, and I integrate over some finite range along this vertical direction. So the green object will be seen as sharp, as being in focus. But the blue and the red object will both appear out of focus, one because it's too close, and one because the other one because it's too far. And that is, of course, exactly the effect that that we saw here. In this case, well, the background was too far. There was, in this particular image, nothing that was too close to the camera. Okay, so we have the lens. When focused on the green object will appear as crisp. Everybody agrees with that? Okay. Now what happens if the lens is focused not on the B plane, but if it is focused on the blue object? The same argument goes through, but we now integrate over regions that are well aligned with the rays of the blue object. So the blue object will not be blurred at all. The green object will be blurred a little, and the red object will be blurred a lot, because I integrate over a region that's almost perpendicular to the rays of the light field. So what we've seen here is the lens this time focused on the blue object. Okay, so there is what your conventional camera does in terms of light field. Now we come to stereo. And I think I have another extra slide. Stereo. We now have two lenses, and in the around 1910 or so, these devices were really popular. So there was indeed, as shown here, a single film plate, but you would have two apertures and two lenses, and you could, in that sense, take images which, if looked through a particular device or in a cross-eyed fashion, would really look three-dimensional. And we have these two lenses. If you remember again what the pinhole camera looked like, this is like two pinhole cameras, except one is shifted to smaller A values and the other is shifted to larger A values. So we now have, if we just had two pinholes, it would be two pinhole cameras, but really we have two lenses. So probably we also integrate a little bit over these directions here. So with a stereo camera, we've now covered more of our light field. However, we had fewer pixels per image. Can we see that in our overview? So the advantage is that we now have, it will now be possible to extract depth information from these measurements by the correlation schemes that we've talked about. So I could, for example, take my gray value measured in this box and then ask where I observe the gray value again. So this would be a poor match, this would be a poor match, this would be a poor match. Then somewhere here I get an okay match, and then I obtain further poor matches out there. And to be robust, you wouldn't correlate a single pixel, but you would take a whole neighborhood, a moving window, and correlate those. But the idea is clear. The price that we have paid is that we now have, for each of these, if we still want to use the same number of pixels overall, we now have a smaller number of pixels or a small resolution per image. So if you compare this with the lens image here, I have 24 pixels overall. And here, so I had a resolution of 24 pixels for this range, and this time I only have a resolution of half that. I only have 12 pixels in that direction. So there's your stereo camera. And now comes the generalization, namely to use multiple cameras together. This has come under a variety of names, light field camera or radiance camera or Plenoptic camera, where you try and capture ideally all of the light field. So we have these distinct sensing elements that each integrate over one part, and you see that in this case the spatial resolution has become coarser still. So here we had spatial resolution of 24, and here it was 8, and no, this was 12, and here is just 8. However, we can now more reliably estimate orientation and hence depth than we could in the case of stereo images. Actually, if I say more reliable, it really depends on the image content, and this is what the paper that I'm citing from is all about. And they conclude that for typical human uses where we want high resolution of our image, but we don't need super accurate depth measurement in most cases, actually a stereo camera is a very good trade-off compared to Plenoptic. Okay, so we have here schematic picture of what a Plenoptic camera looks like. We have multiple cameras built into one, or you actually have an array of cameras. That is also possible. And after the break, I will say how these cameras are actually realized. For now, just two more comments. One is that here we've looked at a four-dimensional parametrization of the incoming light. However, in reality, if we want to capture the full visual content of a scene, we would also have to vary the light source. So you can imagine the light source being a point source, which you move around in space. This gives you another two dimensions. Then you have the BRDF, the bidirectional reflectance distribution function, which tells you if light from a particular direction hits the surface of an object, how does it bounce off? So do you have a matte object or do you have a specular object? And for most objects, actually there's also some subsurface scattering. So if you look at a glass of milk, this is the typical example for to illustrate the quality of a graphics rendering. If you model a glass of milk without the subsurface scattering, it looks just like a block of cement, not very appetizing. So the color is right and everything, you just are lacking the scattering. So what you really want to do is you want to characterize how your object looks like if light from a point source, if a ray enters in one point, and if you measure at another point, what will be the angular luminosity of this emanating light beam. And then on top of that, you should of course do that not for one wavelength, but for all colors. And so altogether, you would have a 9-dimensional entity, 8 dimensions for the bidirectional surface scattering reflectance distribution function, and another dimension for the wavelength. And I'm not sure if I've not forgotten any dimensions. Time, of course, yes, thanks. So this is something that's impossible to measure. You know, we just don't have enough. Even if we could measure it, we wouldn't have enough hard disks to store it. So we need simplifications, and one extreme simplification that's frequently used is the Lambertian model, for example, which says that the BRDF is so that models a perfectly matte object. That's what you mean when you say Lambertian. So the light field, even if four-dimensional and already not so easy to measure or to acquire, is really just a small subset of everything there is to know about a visual scene. And the other comment is that, so after the break we will talk about the Plenoptic camera and then about what is a coded aperture lens and briefly about what is wavefront coding. All right. So the idea of this radiance photography is to measure the energy density in this 4D space, of which we've seen 2D sketches so far. essentially you want to record the entire light field now, and you've seen that, apart from being high dimensional, looking at a light field is perhaps not so terribly intuitive. So you want to record now, but render later. And by rendering later, you can change things like focus or the aperture or the viewpoint and so on, where change of so by changing the aperture, you will change the depth of field. However, by changing the viewpoint, when changing the viewpoint, you're restricted by your most extreme cameras. And if you have a real physical camera array, like the one shown here, so this is the Stanford array, you can achieve pretty large baselines. But if you have all these multiple cameras built into a single one, you're limited by the size of your objective. So viewpoint changes will then be rather small. So I've shown one extreme realization. So this is from the early 2000s, and they needed special streaming hardware and so on to get all this data to disk fast enough. Here's a sketch of more realistic hardware. This is a slide from Todor Georgiev from a tutorial he gave in 2008. And this explains how the micro lenses can be arranged relative to lens and sensor. So there are two designs here, but you can have a continuum of possible designs. Georgiev called his a light field camera 2.0, and in the so-called 2.0 camera, the micro lenses are focused on, so if you put the sensor plane here, then the micro lenses are focused on the imaging plane. So at the location and space where your primary lens gives a crisp but upside down rendering of the original image. And in the more conventional setup, the micro lenses are arranged such that a single pixel on the projector maps to infinity, or here to one part of the entire lens. And so there's a continuum of possible architectures. This 1.0 architecture is one extreme. The other extreme would be to have, to move these micro lenses ever closer to the center and have no micro lenses at all, just a conventional camera. And in between, there are all these possibilities with different trade-offs of spatial versus angular resolution that they permit. So here's what such an array of micro lenses looks like. And here, each micro lens covers multiple sensing elements. So you were just discussing fill factors of detectors. So you have the photosensitive elements, but then you also have, let me do this in 1D. So on a conventional detector, you have these photosensitive elements, but you then also need space for wiring and so on, which is here between these elements. And you can use a lens that will collect all of the light that falls in this Voronoi region and sends it to this photo element. Here the situation is different, so we have multiple photo elements and then a lens, well, and there should be some distance in between these, and then a lens that covers several photo elements. And now you have a trade-off. So the more photo elements your lens covers, the better your angular resolution, and hence the better your depth discrimination capabilities. However, you also reduce your spatial resolution unless you do super resolution computationally. Here is a famous light field acquired by Ng, who was one of, well, back then a PhD student in Mark Lavoie's lab, who made plenoptic cameras popular for the first time, or handheld plenoptic cameras. And shown here is a light field, so really what the sensors in the camera have measured with 3 zoomed out regions. And for this 1.0 camera, the green region should be in focus. And you see that even in this in focus region, the individual images, which consist of multiple pixels, are fairly blurred. And the reason lies in this architecture here. So even something that is in the focus of your big lens will not be mapped to individual pixels on your sensor. So you have to compute the crisp image. And then you have things that are closer than the focus and further than the focus. You see here we have a dark object and a bright background, and things that are closer than the focus have this, these are like looking through tiny lenses, but you have the dark versus bright pattern as you would expect it. And here you have a bright region here and a dark region there, and the patterns are inverted. So here we're further away than the focus, and all of these small images are inverted. Here's a light field from a 2.0 camera. This light field is by Georgiev, and down there you again see what the camera has really acquired, and there's a seagull, with an eye and a head and so on. There's your seagull, and here is zoomed in what was actually measured. So it's like many cameras that are slightly displaced with respect to each other. And in these pictures you can already guess how one would move about the observer. So for example, I can now remember that somewhere I have the lens of my system, and I can now virtually build an observer that looks only, for instance, through the upper left part of the lens, or that only looks through the bottom right part of the lens. To get those parts, we would have, now I have to guess this resolution here. I'm guessing that this is maybe 50 by 50 pixels. Let's say this is 50 and this is 50. So this corresponds to a 50 by 50 tiling of my entire lens. Now, I'm running out of patience, but imagine 50 of these. No, so here, well, each of these small pictures is just a normal picture. And so there's nothing fractal or holographic or so in here. And I now want to create an artificial observer looking at this scene, let's say, from the bottom left corner or from the top right corner. And to synthesize this observer, it is now possible to pick out the corresponding pixels. So for example, if I take the bottom left pixel out of each of these images here, and I hope you can imagine that if I do that for all of these images, I will eventually assemble a complete image, and this would correspond to all of these pixels taken together can be assembled into an image. So let's say these pixels which I just collected here can be assembled, if I put them right next to each other, can be collaged into a small picture, namely a picture which sits somewhere, in this case in, I'm confused now if it's top right or bottom left corner, but in one of the extreme corners. And similarly, by picking, one of these, by picking, for example, the center pixel in each of these patches, I could create an observer, a virtual observer that sits or that looks through the center of my lens. By taking a picture in the pixel in the corner, we've created a virtual observer that looks through just one of the corners of the lenses, of the big lens. So when building such a Plenoptic camera, I can only move around my observer as far as my aperture permits. Now on the hardware side, there are many variations on this theme. I can, for example, use different sorts of micro lenses. I could use micro lenses with different focal length, for instance, which is what the Raytrix company does. So if we look at three adjacent micro lenses, they are not the same. Let's say this is type 3, type 1, and type 2, and then it repeats. Type 3, type 1, type 2, and so on. So this is like combining several cameras with different focal length. Or we could change the absorption of these different microlenses. So looking from the top, assuming that they are arranged in a square grid, which need not be, they could also be on a hexagonal grid, I could make some of these micro lenses very dark, and I could make some of them bright. Now I need to think of some good, no, this is not a good pattern that I've started, but let me just do this in one dimension. Okay. In this way, you could combine, in a way, cameras with different exposure times that allow you to do HDR photography. Or you can use micro lenses with different polarization, for example, or whatever else strikes your fancy. Here's a picture from a paper by Christian Pervas, so one of the founders of the Raytrix company, that illustrates the principle that you can recombine those individual measurements to refocus your image on an arbitrary surface. So you could refocus on planes, which people have been doing for most of the time, but assuming that this would be that the surface shown here, this irregular surface shown, would be the surface of an object, it is possible to refocus your camera on each point of the surface. And Georgiev would not like the word refocusing. He says that so far we've just acquired the light field, and it is just focusing it at different parts. So focusing in the first place. So let's look a bit at this refocusing. For that, we need to settle on a parametrization. And the two parameterizations that are most frequently used are, on the one hand, the two-plane parameterization, which is the one that I've mentioned before. So you have, let's say, a coordinate u and a coordinate v. And that allows you to specify which ray we're talking about. Or we have the location angle parameterization, which is a bit of a misnomer because really it's the slope that people look at, but it's called location angle in the literature nonetheless. So if we have some, let's say we have the same ray here, we can now look at this ray from two orthogonal sides. And measure each time the slope that we perceive in a parallel projection. And this is the parameterization we're using now. So if I want to refocus, I need to compute how the light field is transformed by propagation through space. We have the optical system of optical axis of the system here in this 1D sketch. We have some position and some slope. So let's say this is position Q and slope P. And let's assume that we have measured the light field here. And if we wanted to compute our image for the, if we wanted to render our image at position Q for the current setting of the lens and so on of our system, we would take the radians and integrate over all these different angles. So here we integrate out the slopes from our radians. And this gives us a classical 2D image. But now we want to refocus our 2D image to a different location of our sensor plane. So what we need to find first is the radians that we would have measured at that other location. And this ray here, which was originally at Q and P, now moves to a place Q prime, which is the old position, plus the slope times the distance by which I want to move. So this is transformation distance t, and the slope remains the same. So I can say that this propagation through space has the following effect. I get a new q prime and p prime, which is a simple function of the old q and p matrix with 1, t, 0, and 1. So this matrix here encapsulates the effect of propagating the light field through space. And I can now compute a new image where the sensor plane has been shifted by t. Which is the radiance at these new locations. So I want to use q and p again, so I can solve this here for q and for p. So this is my 2D image after shifting my sensing plane by t. And there you are. Now this looks very attractive because overall what happens is that we're trading spatial resolution in these light field acquisition devices for angular resolution, and we have plenty of spatial resolution these days. So Nokia is putting out a new phone which has a 40 megapixel sensor, but who needs 40 megapixels in a snapshot? So it would be possible to instead use a microlens array and gain some angular resolution and then refocus after the fact. So really acquire light fields, not images, and then render the images. One probable limitation of this is that it is difficult to manufacture these things to be super shallow. So, this geometry here for light field camera, you want to make it no thicker than your current smartphone, and that is a bit of a challenge to make them small enough. Actually, the 40 megapixel chip in itself is already pretty large, so these early high resolution models seems to have a bit of a bulge to accommodate this huge sensor. So that's about refocusing, and I think I have pictures, yeah, for the relocation here. Yeah, I agree. So the attraction in acquiring light fields and being able to refocus and so on is that in principle you could do without any moving parts, and moving parts are always a source of errors. And here you could always take these images with maximum aperture and then afterwards re-render. And here's a slide from again Todor Georgiev from a CVPR 2008 tutorial showing how this viewpoint rendering can be achieved. So in this case, all the blue pixels would be assembled. So this is the big box shows what you see, what is the raw data your sensor has measured. And now you collect all the blue pixels into a smaller image, which out of the whole plane, in this case, you emulate a 4x4 array of cameras. And if we take this particular pixel here, we emulate a camera looking through this part of the lens. And here we emulate a camera looking through that part of the lens. Okay, so it's in a way it's a generalization of stereo imaging.